Hi everyone, and welcome to the section 6.3 method. This is on the shell method. So we're still going to be doing volumes of revolution. We're just introducing a new method that can help in certain scenarios. And so to understand this method, we're going to look at this example that just comes straight from the book, but we're going to kind of try to dive into it a little bit. And it's going to be an example here where we see the picture. The function is y equals 2x squared minus x cubed. So we're just looking at this picture here. And we're cutting this at y equals 0. And then what we're going to do is we're going to rotate around the y-axis. Okay, so that's this here. We're circling around. Now, if you were to draw this out, right, you would do what we had done before. So this was in the previous section where I'm going to just kind of do a quick draw of this picture. Right, we've got something that kind of goes up here and then kind of comes down like this. And then what did I say before? If we circle around this way, just take this and rotate it 180 degrees. So we're going to try our best to kind of replicate that. Might not be perfect, but that's pretty good. Okay, so again, this is just me taking that first picture here and rotating it 180 degrees. Now, what's the gut reaction that you may have built from the previous section? Looking at this, it's the y-axis. So your first gut reaction would be, okay, that means since I'm going around the y-axis, I'm going to just pick a specific value here, a y value, and then I'm going to draw in a washer, right? A washer because there's a hole here, right? There's a giant hole. So there's a washer that just kind of remind you of a shape. That's the shape that's sitting here, and it's just slicing through these two humps. So that's from the previous stuff. That would be a good intuition to have to do. But here's the problem. How did the washer work? Well, the washer worked by us needing some inner radius and an outer radius. Okay? Now here's the problem. Remember, we picked a y value for this, right? So that means that because we picked that y value, I'm thinking, let's do dy, because that's what happened before. If we were doing this washer method and we went around the y-axis, we were going, okay, let's do dy. Well, here's the problem. We cannot take this function here and solve it as x is some function of y. This is not going to work. Okay? Because when I pick a y value, there's actually two numbers I get here. So, right, I give a y and I get here and here. So I can't just solve for one function. Now, what we could try to do, just for completeness here, is say, okay, well, this breaks down because if I was x as a function of y, this won't pass the vertical line test, as we see here. And again, I know that sounds weird looking at this picture, but remember, when I say x as a function of y, you got to turn your head. Remember, that's that idea. If x is a function of y, you should be turning your head 90 degrees to kind of try to see what that looks like. So that's not going to work. Now what you could do is say, well, maybe I'll just kind of slice this and kind of take it as two different pieces. Then I can define this chunk of blue here, x is some function of y, and then I'll have a separate function here. And then it's like really starting to get crazy, and that's just so much. Like, no good. So we need a new method to deal with this situation. The situation where you set it up, you're like, okay, I've got what I want to do, but I get to washer, and I can't really solve x as a function of y. This is not something that is something I can do. So what's the thing that we need to do here? We need to develop a new method that gets us into dx's. That's the whole point of the shell method. So let me just reiterate that because it's a very important piece of this. The reason we use the shell method is because here dy is no good. So the shell method comes in this scenario to get us into dx's, and we're happy. Because look, y is a function of x. So if I could be in dx's, I'm feeling real good here. Like, I'm real happy. So that's what the shell method does. Very simply. It gets us out of this dy scenario, y as our variable, and gets us into an x scenario, which you'll see in the picture in a second, kind of how that works. And you will see in an example later that this works for the other direction too. We'll see an example where I'm rotating around the x, which if I'm doing this, just washers and discs like in the last section, I'd be dx, let's go. But maybe I have a function that I can't solve for x's, and I'm like, oh no, that's not going to work. I use shell, it flips to dy, and it's going to work. So key point here, the shell method lets us take a dy situation, like this picture, and do a different thing so that we're in dx's. Okay, so what is this method? Well, it's called the shell method. It's just a shell. I'm putting cylindrical shells in instead of washers or discs. And so you might look at this and be like, well, come on now, didn't we just have cylinders? Like, I just drew this, which, remember has the little bit of thickness here, so that we kept saying this was a cylinder. So you might be like, why is this different from a washer? Here's the key difference. The small change, right? Before, we were calling this thickness dy, right? So let me zoom in here a little bit more because I'm drawing something small. So in the previous washer disc method, in this scenario, we have a thickness of dy. Okay, but now over here, I do not have a thickness, a up and down thickness. See how this is the vertical piece of the cylinder? That's my tiny thing, thickness that's getting smaller and smaller. That's not happening anymore. H here is no longer this really tiny thickness to the cylinder. No, the vertical thickness here is replaced with H, and now the thickness comes in the actual top part here. So this part here where I'm making my circles, this is not necessarily very small. It could be big. It's the radii of the two functions you're looking at, right? But here now, our little thickness is no longer vertical, but it's in the horizontal. So the change that happens here is, instead of the thickness of this washer or disc, depending on which one we're looking at, being this vertical one, now we translated it into a horizontal thickness, which is, hopefully you can see, like, oh, the thickness was dy, so I'm doing y's. Here, in this case, the thickness will be in terms of x now. This will be x's, right? This is all going to be about x's. And so look, we just now have dx, where before we would have had dy. So we've translated that thickness of the shell from the vertical in the washer disc now to the horizontal. And that's the key. That's what gets you from y's to x's in this scenario. So let's see how this would look. Okay, so this is what a shell will usually look like when it's sitting in a function. Okay, we will have to determine the height, which very often just directly deals with the function f of x. Okay, and then what else do we need for this formula? Well, if you go back up here, you can see that they go through what the volume of the cylindrical shell will be, and it's actually not too bad. You basically just do what you did for the washer. You think of this shell as being kind of a combination of two: a solid, bigger cylinder filled in minus the smaller one. That's what they're doing here when they do this. They say, okay, take a solid outer cylinder minus the inner cylinder. Okay, and so they start working through this and working through this. And when you get to this point, it's kind of neat. This picture is trying to illustrate the fact that to find the volume of this, all you have to do is take a pair of scissors. So here's scissors. Wow, great scissors. And you take the scissors and you just cut the cylinder. So just picture a cylinder. You snip, 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 cut it along some line, whatever line you want, and then you unfold it, and this is what you get. So scissors, you cut it, and then you unfold, and you get this picture. This and the cylinder are the same thing. It's just I snipped the cylinder and unfolded it. And what we want to do is figure out the volume of this, but this is pretty easy to do the volume of. It's just this prism, right? So that would be its length times its width times its height. Well, I can figure this stuff out. It's a circle on top, right? So I know how to do this length here. It's the circumference of the circle, 2 pi x, because x is the radius here. Then the thickness, remember, that's your delta x, because remember we've transferred, instead of dy, now we are in this dx scenario. The thickness is now an x thickness. And again, I'm picking x's now. That's the whole point of this. And then the height, well, the height in the scenario is always going to go up to the function. Okay, so then f of x. So when looking through this, and it does a nice job here, the 2 pi x is the circumference of this cylinder we're putting in. The height of the cylinder is f of x, and the dx represents this thickness here. And that's our formula. 2 pi x, f of x, dx will be the formula we use in a general scenario when we are going about this axis here. Now, if we go about the x-axis, we're going to have to change the scenario just a little bit. And if we go about an axis that's shifted off, like we had seen in the last video, then we're going to have to just adjust for that, like we did again in the last video. So a little bit weird possibly, but once you see a few examples, I hope it's not too bad to kind of get through this, okay? And so just going back up to that previous picture now, what we're doing here is we're saying, okay, shell method, how does this look? Well, how this looks is I say, all right, well, let me get a good color. Let's do this brighter color. So how do I apply a shell here? Well, instead of picking a Y and trying to draw in a disc or a washer, I am now going to pick an X value here. I'm picking an X now, which is the whole point. Get rid of dy, get me X. And at this X, I am going to draw in, let's see if we can match this up. I'm going to draw in this cylinder that's going to cut through. And again, it has a little bit of thickness, right? I'm going to get this cylinder that is going to cut through my solid. So I got this cylinder here that cuts through. So this cylinder, and the picture's not great. There's going to be visualizations and the additional resources that are way better than the pictures I'm drawing here. But what you got to think is, as I move X, my cylinders are going to keep filling up. As I move X out here, I get just wider and wider cylinders that are going to fill up this whole solid. And so, okay, that's good. We can fill up the solid with these cylinders. We still leave a hole in the middle, so that's all perfect. But now we're in terms of X's here. All right. So that's what the picture will look like in general here. So okay, let's go down and do an example. Get you some nice pictures in the example. So we've got this example here. Y equals 3 plus 2x minus x squared, and x plus y equals 3. So first thing we do is we do a little graph. Okay. Right now I'm in y equals a function of x, so we'll just leave that for now so that we can kind of, get our picture. And so this again is a parabola. It's going to be facing down, right? So it's good. This just off the top of our heads, we're going to get this. This is a line. Y equals, and then you could just move stuff around. This is y equals 3 minus x. We don't know if we're doing things in terms of x yet, right? We just are just thinking about kind of how this looks and trying to think through it. So this will be a line, and it'll have a negative slope. So it'll be up here at 3 and then have a negative slope. So it'll look like that. And then if you do the graph out, this is what you'll see. So this line here is y equals 3 minus x, and this is the parabola, 3 plus 2x minus x squared. Okay, so that's y equals 3 plus 2x minus x squared, and this is y equals 3 minus x. Okay, so right here we see this region, which is our original region, and then we have rotated it 180 to get this region. So we can draw our picture. Okay, what about the bounds? Well, how do we figure out the bounds? Remember, we just have to set these equal to each other. So that's 3 plus 2x minus x squared equals 3 minus x. So I'll move everything to the right-hand side, just because I like a positive x squared. So 0 will equal x squared minus 3x. And then, luckily, the 3 and the 3 here cancel. That's pretty nice. So I just get this. That's x times x minus 3. And so they will intersect when x is 0 and when x is 3. Boom, boom. So, okay, great. So, all right, I've got my region, I got my bounds set up. Now, if we were in the previous section, I would look at this and go, okay, I need to be doing a washer. So let me just have you think through this, because one of the things you need to do in trying to understand this is to convince yourself why we need shells here. I think that that's a good thing to do. So what if we wanted to use washer here? Well, okay, I'm rotating about the y-axis. Okay, so if I'm going to do that, then that means in this scenario with washer, I would be immediately going, okay, I'm going to do dy. So let's list the problems immediately. Number 1, this function is not in terms of y. It's a function of x. So problem number 1 is I've got to solve this x as a function of y, which does not look good. Okay, what's the next problem? Well, the next problem is try putting in a washer at a couple places and see what it looks like. So, okay, all right, I'll do that. Here is a y value that I would pick for my washer. And so, okay, my washer would cut through here and here. So if I'm just thinking inner and outer radii here, right, because that's what I would need to do for my washer, I don't even use this function. Look, I end up using this function for my inner and outer. And you might be like, well, how do you do that? Well, in order to do that, like I had shown very briefly in the previous video, I'd have to split this right here and define this function, one chunk here and one chunk here. Because again, if I turn my head 90 degrees, this curve no longer passes the vertical line test. So I'd have to split it into 2, and then I'd be able to define this as a function, x equals a function of y, and this one separately, x is a function of y, with one being a positive square root and one being a negative. Totally ridiculous. We don't want to do this. On top of that, I would then end up having to split this another time, because watch what happens right here. I'm going to keep doing my washer. Here is another y value, and I have another scenario now where I do now have an inner radius hitting this line and the outer radius hitting this function. So I would have to split at y equals 3 to a completely new integral where now I'm using both functions. So this is really bad. This is really bad, not going to work well, ton of work. So what do I do? Using x as a function of y is just not the way to go here. So let's try what's called the shell method. So let's try doing shells instead. Shell. Woohoo! So we're going to actually take this picture and copy it so we don't, overload. Okay, so we've got our picture, and now we're going to do shell method, which in this scenario, when we're going around the y, that tells me I should be doing things dx. So, okay, I already have my functions in terms of x's, so that's a really good start. All right, and now we pick an x value. So pick an arbitrary x value. So just to kind of start off so you could see what's happening. Here's some x value. So we've got this x value, right? And we're going to try our best to draw an okay cylinder here. So here we'd go up here, here we'd go up here, and then I've got my cylinder now cutting through here. So here's my cylinder. Okay, so again, this has a little thickness, but just to kind of get us started, we don't need to clutter up the picture with that right now. So we've got this cylinder kind of cutting through here. Okay, so what do we need for the cylinder? Let's recap from the formula. Well, the formula, remember, was the integral from a to b of 2 pi x times the height dx. Now, I just left it as height because this is actually a little tricky way to think about this. This is the height. Okay, so then let's just double check here. This x was the radius. Does that still make sense? Well, let's start here, and actually we'll color code this. We'll make this one green. So where's this x coming from? That's supposed to be the radius. So I say, okay, I go right here, and I go out to this, and oh look, that was just my x value. So okay, cool, that's still the radius, so that fits. What's my height? Well, previously in the above directions, it was just the height of my function. But I've got two functions here, so somehow this height is going to involve both of them. So okay, I look at this now. What's my height? It's this up to this. So how do I define this h? Well, for this x value, this tippity top here is going to be the parabola evaluated at that. But I don't want to go this full distance, right? That's too far. I have to take away whatever this is. But that's just this x value evaluated at the line. So the height in this case actually becomes, so the height here becomes my parabola, which was 3 plus 2x minus x squared. So h equals 3 plus 2x minus x squared minus, and then this line, which, if we remember, was y equals 3 minus x. So the height, again, it's this height right here. Right here. It's the full distance from 0 up to this parabola minus the distance from 0 to this line. I have to subtract the two so I can get just the in-between. So our bounds here, our a and b, are going to be 0 to 3. We had already figured that out. That's the x values we want. So altogether, this is going to be the integral from 0 to 3 of 2 pi x. And then we can simplify this down, right? This is 3 plus, and then 2x plus another x. That's 3x. Okay, and then we've got that minus 3, which will cancel there. And then we've got a minus x squared. So this will go away. So then that's 3x minus x squared dx. And then this doesn't look too bad. You can do some multiplying, but we can also take this 2 pi out. So 2 pi integral 0 to 3 of 3x squared minus x cubed. And this is totally doable. Add 1, divide. So we got an x cubed. Add 1, divide. So we got a 4 there now. Plug in 0 to 3. Nicely, again, the 0 is just going to be 0, so that's awesome. So this is 2 pi, and then we're going to plug 3 cubed minus 3 to the 4th over 4. And we could put that in a calculator to simplify, but I'll let you do that. Shell method. It's really not too bad. You get to this point, it's okay if your gut is like, let's see what happens with washer. But you got to be able to take a few kind of steps. You can do it on paper, or you can start thinking about it in your head to be like, no, this is not going to work. I can't solve this. X is a function of y. I'm going to have to break this into a bunch of different parts. Let's try shell so I can now use x's when rotating about this axis. Okay, so let me give you a little kind of like all together piece here. When you're rotating, so here's the little thing you can kind of try thinking about. When you rotate about the y-axis, or any vertical axis. So I can do like x equals 1 as an example. Right? Here's what happens. Disk and washer from last section are going to be dy. Shell will be dx. So if you get into the scenario where you know you're rotating about the y-axis or any vertical, what you got to do is you got to say, okay, what's going to be better here for me to be using y's or x's? If you can make that determination, which isn't too bad, kind of using some of the ideas we had above with solving one function for one variable and so on, then this can just tell you what you should use. That's it. So if we rotate about the y-axis or any other vertical axis, if I'm okay using y's in my radii, my heights, or in this case just my radii, then let's go disk washer. If I'm like, no, that's not going to work, then we can use x's, but it's going to be the shell method. All right, let's try another example. Okay. So in this case, again, I'm rotating about a vertical axis. Here we go. But I'm shifted. So let's see what happens here. So we've got x to the 4th, y equals 0, and x equals 1. And I'm rotating about x is 2. So here's my x equals 1, kind of slicing. Here's my x to the 4th. So this is y equals x to the 4th right here. This is x equals 1, kind of cutting me. And then we got this is our region. Okay. And then this is x equals 2. This is our axis of rotation. So I'm rotating around here. So what's the first step? Draw the 180 rotation over here. That's always a nice step to do. Okay. All right, so again, first gut reaction could be you're trying washer, right? Right away though, if I'm doing washer, that's dy. So if I'm like, okay, let's do washer, that means I'm doing dy, which means I need to solve this x as a function of y. But you might already be like, I don't want to do that. So okay, in that case, try something else. And I'm not saying you can't do that. You totally can do that. You can use washer here. That's fine. It's not a huge deal. You can definitely do that. But, it says use shells, so let's just use shells. So instead, shell, you're going to be using dx. So, okay, great. It's already a function of x, so that's not too bad. Okay. So then what do we need? Well, remember, we need the radius and the height of the shell. So let's just draw in one of these so that we have it for reference in the picture. Let's pick an x so we don't get too high up. Let's pick our x here. Okay, so then I'm going to hit this point. All right, and that is going to then go all the way over here. Right about here. And then this is going to be shooting over. And then there we go. And then and there's my shell. Not the best shell, not the worst shell. So there's my shell. So this is good enough to figure out things like the radius and the height. So in this case, we'll start with the height. So the height here is just this. This is h. So it goes from 0 up to bonk. What did I hit? I hit the function. So okay, that's pretty easy. The height's just x to the 4th, right? This height here is just, I start at 0 and then I boom, bopped into the function. Okay, so then I need the radius. What's the radius is going to be? Well, the radius is a little trickier. Let's make this a different color so we have some good vision on this. I have like 1,000 colors over here, but for some reason it's always hard to choose. We'll make the radius this brighter pink. Okay, so I start here at the axis of rotation, and I just travel all the way until bonk, hit that. Okay, so what did I just go? Well, I'm at 2, okay, but it's not a full 2, right? Because I didn't go all the way to the axis, so it can't just be 2, but it's going to involve 2. Okay, it's 2 minus, now what's this distance here? Well, this distance is just 0 to x. So it's just x. So this is 2 minus x. This should look awfully familiar to the last example we did on the last study guide for 6.2. So I'm just, same kind of idea here. This shift just happens when I move my axis of rotation. All right, so that's not too bad then, hopefully. So, okay, we've got then to do the integral from a to b, we'll figure that in a second, 2 pi, my radius, times my height, dx. Now, how do I figure out exactly where I'm going? Well, if we look at this picture, right, y equals 0 is this baseline. Well, okay, look at the function here, right? When y equals 0, this tells me that x is 0. So, okay, that's not too bad. And hopefully that's not too bad to see that this is going to hit here. And then I stop at x equals 1. So, okay, there you go. Those are the bounds. 0 to 1 are the possible x values for me to pick. Okay, so let's do this integral. Take out the 2 pi, 0 to 1. Multiplying here is 2x to the 4th minus x to the 5th dx. All right, we can do this integral. It's not too bad. So that's 2 pi. Remember, add and divide. So this would be 2x to the 5th over 5 minus x to the 6th over 6. 0 to 1. Woohoo, the zeros will come in here and cancel. So this is 2 pi 2/5 minus 1/6. Okay. This isn't too bad a one to do in our head, so we can do this one kind of quick. Combining these fractions, we got to make this 30 because these don't share any factors. So that would be 12/30 minus 5/30. That's 7 over 30. Okay, which is 14 pi over 30. And there you go. So, recap. Washer. I'm too lazy. I don't want to make this x as a function of y, so get that out of here. Shell. Okay, find the height. Oh, well, the height of this is just 0 up to my function. That's not bad. Radius. Ooh, I shifted, but it's not too bad, hopefully, to see that I don't go the full 2 out here. I go 2 minus whatever this distance is, which is just x. Plug in. I can do this integral. We do it. We get our answer. So in this example, we are going to be rotating about the x-axis. So let's talk a little bit about what kind of happens here. What's the general thing here? Well, when rotating about, oh, I lost my R. There it is. When rotating about the x-axis or any horizontal axis, right? Because I can shift this just like I did the last one. Here's what happens. The disk or washer method, right? Well, what's going to happen here? That, in this case, if I want to do a disk or a washer, that's going to now be dx, and the shell will be dy. So again, we get to this problem and we just have to ask ourselves, like, okay, you know, what do I want to do here? Do I want to do shell? Do I want to do disk? What's going to be best? Okay. So we look at this and we say, all right, I'm going to look at this very quickly and determine what to do. I do not want to try to make this x as a function of y. No way. Get that out of here. So then I would really like to do whatever method lets me keep things in terms of x, which is ding, 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 the disk washer method. So I'm very quickly kind of saying to myself, you know what? I'm just not messing around with this. Let's do disk washer. So, okay. This is going to be a disk washer. So that means dx. So let's draw in a typical picture here. So here's my x as an example. Okay, so here's my x. So then I have, up here, I can draw in my disk. Why am I saying this is a disk? Well, there's no holes in this. I rotate this down here, and it fills up the entire area. So there's the rest of the disk, because there is, remember, a little thickness there. Okay, so what's my formula for the disk method? Well, if we remember here, it'll be the integral from bound to bound, which we have to figure out. Do that in a second. And then remember, it's pi r squared dx, because we're in x's. Okay, what's our r? Well, we got to think about that. So our r in this case, start here, travel up, 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 and then bonk, hit the function. So in this case, r is just 0 to the function, which is just the function. Okay, so hopefully that's not too bad. What are the bounds? Well, I have to know when this function hits y equals 0. So for the bounds, we can do that. Little algebra. The bounds, this is going to be 0 equals negative x squared plus 6x minus 8. I don't like this negative, so I'm going to slap everything with a negative. 0 equals x squared minus 6x plus 8. Okay, and then now I just need to factor this. So two numbers that multiply to 8, add to negative 6. That's going to give me 0 equals x minus 4, x minus 2, which gives me 2 and 4. Boom. So those are my bounds, 2 and 4. All right, so here's my integral. The integral, take the pi out, 2 to 4. Okay, and then it's going to be negative x squared plus 6x minus 8 squared dx, which is not the nicest thing in the world. We have to, multiply all of this out. So, again, yuck, but it's okay. We can do it. So let's write that out over here. This you can fast forward through if you want. So first one's going to hit all the rest. So this is going to be x to the 4th. Then I'm going to go to the next one, negative 6x cubed plus 8x squared. Now this term, minus 6x cubed. Okay, go here, plus 36x squared. Okay, now, so that'll give me, boom, boom, minus 48x. Okay, and then lastly, I'm going to hit the negative 8 with everything, plus 8x squared minus 48x, and then plus 64. So, whew, we've got some cleaning up we can do though, right? So pi integral from 2 to 4, x to the 4th, and then what about my powers of 3? Negative 6, that's all of them, so that's negative 12x cubed, okay? And then what about my powers of 2? 8, 36, that's 44, and then another 8, that would be 44, 52. What about my powers of x? I got a negative 48 and a negative 48. Okay, so that would be negative 96x plus 64. Okay. All right, from here, we know how to do this. Just add 1 divide on each of these. So that's pi times x to the 5th over 5. Okay, minus, and then we're going to have up to the 4th divide, but we can simplify that. Okay, add 1 divide, plus 52 over 3x cubed, minus, and then I'm going to add 1 divide. That's 48x squared plus 64x. Whew. And then we're going to plug in 4 and plug in 2. Altogether, that's going to be 16 pi over 15, which you can go through that and check. So hopefully not too bad. This one, we didn't know which one to use, but hopefully quickly we identified we've got to just go with dx here because we don't want to try to solve this x as a function of y. So immediately disk washer.